Okay, hello everyone, and today we'll be looking at doing a definite integral algebraically and getting an exact form when we're looking at actual algebraic processes that involve the natural log. So in order to do this, we're going to start by actually reading the question. This is a question based out of the study guide. But what it actually says, oops, sorry for shaking the camera there, it says find algebraically the area enclosed by the graph f of x is equal 1 over x, take 4 on x take 2, and the x-axis and the lines x equals a half and x equals 1 to 1 on 2. So from there we can see the bounds of the definite integral. We can see obviously x equals a half and x equals 1 on 2, which we can also express as x equals 3 on 2. But what the question also gives us is the fact that we're looking at a definite integral just under the curve. It's not a function that cuts across the x-axis on this interval, so it's just a plain straight definite integral to get that area. So ask us to express your answer in exact form and then use technology to express the area to three significant figures. So we're going to go ahead and try getting it in exact form. So we're looking at the definite integral, obviously for the function f of x, so 1 on x take 4 on x take 2, between 1 on 2, that's our a value, the lower bound, and the upper bound is 3 on 2. So that's our actual expression that we get from this. So what we can do is we know that obviously a simple integration rule is that if we need to integrate 1 on x dx, it's obviously going to be ln x plus c. So we can go ahead and we can, of course, integrate the first part of that. So our capital F of x, which is obviously the antiderivative, is going to be ln x. And then we need to integrate the second term here. And what you could do is you could use a common ln rule, because this does actually turn out to be an ln-based answer as the integral. But if you didn't know that that was going to happen, you could always use u substitution. So I'm going to go ahead and show you how to use u substitution here. Obviously you'd pick the one with the highest power. This is x to the power of 1. There's x to the power of 0. So of course you're going to want to pick the denominator as u. You're going to have u equals x take 2. And then you want to find du. And du is of course just 1. Du dx. And then what we do is we say, well, okay, that means that 4 du equals 4 dx, which is, of course, the numerator. So we can write this as we're looking for the expression of 4 on 1 on u du, because, of course, u's in the denominator. And we know, hang on, 1 on u with respect to that independent variable is, of course, going to be ln x. So what we get is we get 4 ln u plus c. And in there, we just go 4 ln, and then u is obviously, from what we got before, x take 2 plus c. And so we can finish off our integral expression by writing 4 ln x take 2 plus c there. Okay, so now what we can do is we can go ahead and actually evaluate it, because of course we know based on the Fundamental Theorem of Calculus that if we evaluate it at the upper and lower bound, then we're obviously just evaluating the area. So we can go ahead and actually evaluate. That's the next key step here. So we're looking at, first off, I'll write out the two actual ones separately, but we'll then work on doing the subtraction afterwards. But if we're looking at the antiderivative evaluated at 3 on 2, we of course have ln 3 on 2, again just plugging in 3 on 2 as x into the antiderivative, lots of 4 ln, and then 3 on 2 take 2 plus c. And there's our f of 3 on 2. But our next one, which is our antiderivative at a half, is going to be ln a half take 4 lots of ln a half take 2 plus c. And then what we have is we can actually have the upper bound subtract the lower bound. So what we can do now is if I just tilt the camera down a little bit further, but what we can see is that we're going to end up with ln 3 on 2 take 4 ln, and then we've got 3 on 2 take 2, so that's the same as having 1 over half take 2, so we're going to end up with a negative a half, but of course we've got the modulus sign, so it's always going to be a positive value, so we're going to end up with ln a half there, plus c, and then it's going to be take ln a half. Again, we're just pulling it out of here. It's just that expression there that we're putting in. Take 4 ln, and then a half take 2 is going to be negative 3 on 2, because again, it's like having negative 1.5, so we write that as 3 on 2, of course, because it isn't negative. And then we just don't worry about the c's, because they obviously cancel off when we're using the Fundamental Theorem of Calculus. So for the next step, we just need to simplify this down a little bit. So let's see what we've got. We've got ln 3 on 2, and we've got another ln 3 on 2 here, and this is actually plus, because if we remember, it's that take there, and obviously if we have a take sign there, and we've got another take sign here, it's going to be a positive when we actually write it in the expression. That's the key thing to be careful of with the algebra. But when we're simplifying this, we can see we've got ln 3 on 2, ln 3 on 2, so we've got 5 ln 3 on 2, and again, this is the f of 3 over 2, take the antiderivative of a half, but we've got 5 ln 3 on 2, and then we've got negative 4 ln of a half, and then we've got negative ln of a half, so let's take 5 ln of a half. Again, just joining like terms like you would in algebra, and now to simplify this, to get it into the exact form specified in the question, we can say that the actual definite integral, which again is just equal to the antiderivative at the upper bound, take the antiderivative at the lower bound, is going to be equal to 5 bracket ln 3 on 2 take ln of a half. And then what we do is we can simply take it to the next step and use the technology to express the area to three significant figures. So if you head on to your calculator here, you can see that I've typed in, I've just done 5 ln 3 on 2 take 5 ln a half, and we actually get 5.49. So of course we're going to three significant figures, so we chop it off there, and we just end up with 5.49. Now we need to remember units. Of course, we're looking at area, so that's going to be units squared, and we can also express this one as unit squared as well, because we're looking at the context vary of both. It doesn't say to find the definite integral, it says to find the area enclosed by the graph, those bounds, and the function. So hopefully this was easy enough to follow. If you have any questions, post them below, any comments, but that's just looking at doing the definite integral algebraically to find the area under a curve and find an exact value. Thank you for watching, and I'll see you later.